Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm very happy to have Stephanie Telex visiting us here today and giving a talk. Stephanie has a PhD from MIT Media Lab, and she's done work at CSAIL also, I think. She's done fabulous work in grounded language with probabilistic models, and now she's at Brown, and she's going to tell us more, I think, about some of her more recent work on human-robot collaboration.
Thanks, Dan. All right, and we're a small audience, so if there's questions, please feel free to stop me as we go. So robots are really exciting today because we're seeing a lot of success where robots are operating in complex real-world environments. So this is an example of a robot I worked a lot with at MIT. It's a robotic forklift. So it can drive around in warehouse environments. It can sense objects like pallets and trucks and people. And it can autonomously move things around in these environments. It can pick up pallets and unload trucks and stuff like that. We also have robots that can assemble IKEA furniture. So this is an example of a team of robots collaborating to do that with a person, developed by Raster and his collaborators at MIT. And they can make a plan to assemble a complex thing, like table in this case, out of smaller parts. Multiple robots work together in order to carry out this task. And we have robots like the PR2. This is my son, the PR2, back when he was littler. Some of you met me or interacted with him at the MSR workshop. This was right around that time. He's now about this tall, 2 years old. But we're also imagining that there's going to be robots operating in our homes, so in our hospitals, in our offices, carrying out complex tasks, things like helping us cook or fetching objects for us, or maybe interacting with our kids and taking care of them. So as we have robots that operate in complex real-world environments, it's really important that we create ways for them to not just interact with people. People talk about human-robot interaction, but you can interact with a rock, right? So I think it's important to try to go beyond just interaction and think about collaboration. So how can the robot and the person collaborate so that the robot can meet the person's needs? The robot can do what the person needs them to do and help them solve problems in these real-world environments. So what I'm going to talk about today is sort of three sort of thrusts that we need to address to achieve this vision of robots operating in our daily lives. And there's this, Bill Gates said we need a computer in every desk, and then later he said something like robots are going to be in every room, in every house. Everyone's going to have a robot in the next 20 years, I think. Just the way that our computers have moved from a big mainframe to a desk to the cell phones in our pockets. We're going to see these platforms get smaller, they're going to get cheaper, they're going to get more reliable, and they're going to be part of our daily lives. So I think it's really important to create mechanisms for them to collaborate and operate with people. So the first thing I'm going to talk about is making robots that can actually operate in these real-world environments, because we don't just want them operating in sort of fixed, prepared workspaces. We want them in our homes and in our hospitals so that they can do things to help us. And then a second challenge is once you have a platform that's capable of actions, of a large space of possible actions in complex state spaces, there's a sort of AI planning problem. How do you figure out what to do? If you have, 10 things you could do at every time step, and then, you're trying to plan over a course of a day, things you're going to do that help the person, the planning problem, the branching factor, and the search depth is huge. And people effortlessly use language to command you to do things at all levels of this hierarchy. So for example, for the forklift, people would say things like unload the truck, this very high level action that might involve 10 or 20 pick and place actions. And the next breath, they'll say, move backwards about 6 inches. Move out of my way, tilt your forks back a little bit. These are examples from human-human interaction. And people have no trouble with that. They kind of jump up and jump down. But for a robot or a planning algorithm, if you give it that low-level state action space, you've basically made the high-level action, like unload the truck, impossible to find because the search depth and the branching factor are huge. And yet, if you take out the low-level actions so that you can find and operate in some more abstract space, then you can no longer, it's just not possible to move forward 6 inches because there's no action to do that. So we're trying to create algorithms that can efficiently plan and operate in these types of state action spaces. So then finally, once you can operate in real-world environments and you can plan and then plan complex actions, then you have to be able to figure out what people want. So the last thing I'll talk about is coordinating with people, observing what they're doing, observing the gestures that they're making, the words that they're saying, the actions that they're taking, and then trying to infer what they want so that the robot can carry out actions that help them, that collaborate with them. And in particular, what I'll talk about is trying to work towards establishing a social feedback loop between the human and the robot. So it's inevitable when you're interacting with a person because of the perceptual uncertainty and all of the size of the state action space that the robot is going to fail to understand them. And what I think we have to do is kind of embrace that and think of mechanisms for the robot to actively detect these failures to understand and take actions to correct them. And also work with the person to convey what they don't understand. What specific parts of what the person is saying and doing do they get, and what parts do they not get? So they're not just saying, I don't understand, I don't understand, I don't understand, to the person, but you're actively zeroing in on those parts that the robot didn't get, so the person can provide targeted information to get the robot unconfused so that it can move on and go on and do the thing to help the person. So it's sort of a motivating example. This is a scene from my parents' pantry in the kitchen. And what I'm thinking a lot about is as a sort of base capability for a robot is pick and place. So picking something up and moving it somewhere else in the world. And you might imagine a robot that's assisting you at cooking a meal, for example, and you're stirring and you don't want the onions to burn. And so you say, oh, can you please go and get me the pepper? Or you're making a souffle and it's like the delicate folding operation and you need the Parmesan cheese. So it's going to go and hand you you say, please hand me the Parmesan cheese, and it goes off and finds it and picks it up. So object manipulation in robotics is a very challenging, unsolved problem. So robustly knowing about all of these objects in a scene like this, knowing what words people use to describe them, and then more than that, doing pose estimation to figure out where to put your gripper is a really hard problem to solve in robots. So to approach this problem, so this is an example of like handing something off, like a tool, like a knife, for example. So the way that we're approaching this problem is by taking an approach inspired by mapping objects. So inspired by robot mapping. So the real problem that you'd like to solve is you bring a robot into an environment that it's never been in before, some kitchen, and have it look around and see stuff, and then say, hand me the knife, or hand me the eggs, or something, and have it work. But we think that's too hard for right now. So instead what we're doing is saying, the robot's going to come into an environment, it's going to be handed some objects, and it gets a chance to explore, build maps, learn about those objects. And it can do that for a while. And then after that exploration process and data collection process is complete, then we're going to try to manipulate the object and interpret commands about these objects. So in order to do this, you have to know what the object is. So for example, as a ruler, you might want to know a label like ruler. You want to know which object it is so you can load up all the information that you've collected about that object. You need to know where it is in the environment. So here, we're going to label it with the pixels in the image that are sort of associated with this object. But you also need to know like where it is in the real world, right? Because you need to move your gripper somewhere to try to pick up that object. And then finally, you need to know where you're going to actually put your gripper on the object. So in this example, for this ruler, a good place to grab is in the middle because it's kind of heavy, and if you grab it near the end, it's going to slip out. It's going to slip out of the robot's grasp. And existing approaches to this problem are found in sort of two categories. So the first is sort of category-based grasping. So the idea is that you look at the object with your sensors, and then you try to infer what category it is and where you can grab it. And there's lots of papers about this. It's a very interesting and hard problem, and they have tables of results. But when you actually try to run it on your robot with your objects, like we do a lot with like objects that are used in childcare, like diapers and Vaseline, and nobody's tested these models on those objects. And they don't work, and they need more training data, and then you know, you're sort of in this problem of trying to get somebody else's code.
Do they work well on the glasses and dish where they were trained on?
Yeah, so numbers in the papers range between 80 and 90%. The standard right now is you pick your favorite objects and test on them. So one paper will evaluate on their favorite objects, and another paper will evaluate on a different set of objects, and that's just changing. So like, like in the past month or two, the community who's working in this area has created a standard set of objects which you can order, and I've ordered them. They offered them to me early, and I still haven't gotten my set. So like, of about 100, it's about 100 objects that you can then, if we all have the same 100 objects, then we can evaluate on that data set.
And when you evaluate, you're literally picking it up.
Yeah.
You're not just like showing on
different papers. Different papers do different things. You gotta sometimes in these papers you gotta read between the lines. But in many of them, you're actually picking things up, and in our work, we are too.
It's so sensitive that if you have an exact same set but different brands, nothing works.
Yeah.
Yeah.
It's the same, you know, diapers that are, you know, Vaseline, but you switch
Yeah.
companies making them, and
Yeah.
sorry, it's not robust enough for that.
Yeah. Exactly. It's very frustrating.
Yeah, you have like the diaper faction and the plate faction of researching.
I was worried about the Pampers versus the
Right.
Yeah. Yeah. And of course, we all want that capability. Category, like I want to just pull a diaper and I should know it's a diaper and I should know how to pick it up and even unfold it and all that stuff. But okay, so that's category. A second approach that people take is instance-based. So the idea is that you collect images, you have your diaper, it's Pampers, and you collect images of it, you take pictures of it or you put it on a turntable, people will do that, and then turn it around and maybe build a 3D mesh of the object. And then sometimes you can use that to propose graphs. If you have an accurate geometric model, you can get some proposed graphs. There's a lot of work on that. Or you can annotate. You can just say, I want you to graph this object here. That's a good place. I'll just tell you. And it works. So if you collect this data, you can detect the object because you know exactly what it looks like. And if you annotate the graphs, in the worst case, like you will be able to pick it up. But the problem is the data collection. So you need to collect this data, and that's not something you can really expect an untrained person to do or even be willing to do. So Rethink Robotics makes a robot called Baxter that's designed to operate at factory floors, and they have a way for a person to collect data with the robot where they like push some buttons to say, here's the object I want you to pick up. And nobody uses it in the real environment, they told me, because they don't understand why the robot can't see the object in the first place. So our approach is to take the instance-based approach. So we're going to collect these images, but instead of manually collecting images, we're going to use our robot to collect it. So the contribution of this first part is an approach for automatically collecting the instance-based training data so that we can localize the object and then identify the object, localize it, and then pick it up. And we'll actually practice picking it up. So we will propose graphs using your favorite. We have a heuristic method for proposing graphs, but you can plug in your favorite method for automatically computing graph points. We will try them out. And if it works, that's great. We'll be happy. And if it doesn't work, we will do some math and figure out where the next place to go is until we find one that works. And then at that point, we've empirically shown, like through practice, that we found a good grasp. And then we can pick up that object. Okay, so here's what it looks like. I pushed my button, but it didn't go. Just use my, no? Okay. So here's what the scanning process looks like. This is our robot, Baxter. We wanted to use these on the sensors, only the sensors that had Baxter. So what you're seeing is our 1 pixel connect. So this robot has an RGB camera in the hand and also an IR rangefinder, which gives you 1 point of depth data. So we're doing, at the beginning it was doing this raster scan in order to get a point cloud of the object. And then it's moving around to take pictures, and now it's practicing. So this is trying different grasps, servoing in, localizing the object, and then trying different grasps at different locations on the object, and practicing. And then at the end, let's see, so here's what the pictures looks like that it collects for the ruler. Different crops, we crop that out from the background. We get this Raster IR scan. We only need to scan at training time to propose graphs. We don't need it at pick time, or it'd be way too slow. We use just vision to pick. And after we get this data, then, let's see. Sorry, this is showing after the process is complete. This is showing picking these two objects. And the scan that we do takes about 15 minutes, mostly because of the silly depth scan that we have to do, but runs on a stock Baxter. So you don't need any additional sensing on Baxter in order to do this. And we just bought a depth camera that we're going to mount on the arm to try to speed that up. But we're also going to try to explore stereo. You can make virtual stereo because you can move the camera, and then try to get point clouds more quickly from a monocular camera. But anyway, for now we're doing this scanning-based approach. So this is cool. It works on a lot of objects, and you can basically hand the robot our object. We run our scan, and at the end of it, most of the time you can pick something up. Yeah.
Does it work with clothing, which changes shape all the time?
Yeah. So we've tried it with diapers, and it does work.
Infants?
What's that? Infants? Yeah. Yeah, so we are using, one of the advantages of taking this instance-based approach is that you can get away with like really simple computer vision. So we're using SIFT bag of words to detect the object, to localize. We literally we servo in, we take a picture of what it looks like when you're right on top of it, and we memorize the pixels, we compute the gradient of that, and then we measure the error between what we see right now and what that picture looks like, pixel by pixel. So it's nothing fancy, but it works quite well because we have the data, which we are able to collect automatically. And the question about clothing, well, maybe my student keeps wanting to do HOG, which will histogram of gradients, which will capture like the shape properties of objects, but then that probably will not work on something like clothing that's deformable, but maybe the SIFT features will. So we'll have to have ways of like deciding which detection and classification algorithms work the best for individual objects. Okay, so this works on lots of objects. It does not work on all objects. And here's an example of, I should put this down because I guess the battery died. So here's an example of that ruler that I've been using. So here it inferred a grasp based on the geometry of the ruler that got from the point cloud. And what it does is picks it up near the end because it just looks like that's going to work, and it's symmetric. So none of those graphs are particularly better than the other according to the grasp model that it's using. And it's going to do a shake now to make sure it's got a good grasp. And once it does the shake, it pops out because it wasn't a very good place to grasp. The friction between the gripper with the weight of the ruler wasn't very good. And maybe if we had a better grasper system with a better model of physics, a category-based approach could have predicted that, but then there would have been some other problem.
It's not a mechanical thing if you picked it up from the top.
What's that?
If the grip had been from the top, it would have...
If you went to the center, I'll show you, it will work with this particular gripper.
Better model of physics? Do you have any model of physics in there right now?
We do not have any model of physics right now.
So better sound like we have something, but so...
Yeah, so people, yes. So if we had a model of physics, maybe we would learn to go to the centroid. Other things that happen is like you have transparent objects. They don't show up very well in IR. And we hallucinate all these crazy grasps.
Has anybody done any physics analysis? So
yes, yes. There's a program called GraspIt that basically simulates graphs using something about physics and shapes and stuff. And so people are exploring that, but it's whatever you choose, like something's going to break. So this is what's breaking in the one that we're using.
I'm just wondering how much common sense you need in that kind of thing. Can you imagine representing static coefficients of friction between robot hand and object? You can imagine notions of swivel and center of mass.
Yes.
And maybe those two things I would call a deeply physical model, but imagine getting away with a few things.
Yeah. So Josh Tannenbaum talks about the video game engine in your head.
I know. Yeah.
And I think that's probably like the right way to do this. Is to really, like we have some kind of representation of physics, I think, in our brains that we're using to do this. This is something much simpler. We have a proposal system which could use physics or not, and then we're going to just try different grasps and pick stuff up. Now, yeah.
Another place where common sense seems important is fragility, where if it's
Yes.
glass, you don't want to squeeze it tight, but if it's cloth, doesn't
Yes.
really matter probably.
Yes. So we are mostly using objects from my son's toy chest for a reason, because we want the robot to get this through experience, and if you give it something fragile, then it's not so good. Yes?
Does the robot know not to pick up your son?
Not right now. You can see that from the construction of the table, we sort of keep people away through the furniture in the room. Dan, I'm excited to talk to Dan, because then we could do person tracking and stuff, and we could be a little smarter about how safe we are. This is not a mobile robot. I really want a mobile robot. Like my next robotic purchase is going to be a mobile robot, and then we'll have to be more worried about
pressure of the grip. Is it constant, or is there feedback?
Yeah, we keep the force constant right now, and it doesn't. It's basically just the default.
Feedback of
we know,
how
yeah.
much the object is giving as you grab it?
Yes. So we know the position of the gripper and how much force it's exerting. We use that right now to detect if we've successfully picked up the object. So like, it knows it's succeeded if it's achieved force closure. It shakes it. It still has something in the gripper, and then it puts it down, and then nothing's in the gripper because some stuff gets stuck in the gripper, and it tries to put it down. Like if it's deformable or something, it gets stuck. So and that's if you and some objects. One of the ones in our evaluation was a banana. And if you pick it up in the middle, it was like a styrofoam banana because we didn't want to break it. And if you pick it up in the middle, it would always get stuck. But if you did it near the end where it was a little bit narrower, then it wouldn't. And so it would learn to go near the end. So there's basically this long tail of stuff, any one of which you could fix, and people work, and there's papers about probably. The IR, there's papers about transparent objects and how to handle them. But our idea is like, on top of all of that, we're just going to try stuff and keep track of what works and what doesn't work. So for the ruler, when we do this, before the training process happens, you drop the ruler, and here's some examples of like objects that aren't visible in IR. So like this is transparent. This is a salt shaker. It's kind of hard to see in the light, but this is shiny, but a terrible place to grasp. But because of the reflections in the point cloud, it looks awesome. This is where you the handles are where you want, but it's black, so it absorbs the IR light, and so you can't see them. And so we actually learned to move from here to here on this object from experience. So to do this, we formalize this as a Bandit problem in RL. So it's like an n-armed Bandit, where the arms aren't like the robot arms. The arms are different grasp points. So each grasp point and the orientation of our gripper is an arm with an unknown payout probability. You get a payout if you pick it up, shake it, and put it down successfully. And there's like some discretization. And what we're doing is best arm identification. We want to find the best arm given a budget of training trials. So you get to play with the object for a while, and at the end of that time, I want you to tell me the best arm. Yes?
So there's this discretization that implies that the arms are sort of spatially related to each other. Are you leveraging that in the problem?
So in this, right. So there's one more thing that you want to do. So we don't have time to try 1,700 arms. That would take a really long time. Each grasp right now takes about 30 seconds to do. So we have our model that proposes grasps, and we interpret that as basically a score on all of those possible grasps. So we try them in order, and we try them until we're confident above a threshold that it's a good grasp, and then we stop, and we say we're done with this object, we have a good grasp, or we're confident that it's a bad grasp, and then we move on to the next one in the list, in the sorted list. Does that make sense? So because the scoring function takes into account spatial information, the model does. We are talking to Michael, do you know,
if the robot proposes, like if your algorithm proposes two grasps that are very close spatially to each other.
Yes.
Are you gonna, like if I have 5 grasps that are all close here, I wanna, if I figure out this one doesn't work, the other ones are likely not to work, I should move somewhere else.
Yeah, so we do not do that, and I can give you examples of objects where that intuition is false, basically. So like a lot, like there's I don't think I have a picture of it, but there's a vanilla bottle, like little bottles where like it needs to be just right on top, and so the right, like it moves over like one cell basically, and finds it. That said, there's definitely spatial information. So Michael and Ellie Upfall and I are talking about thinking of this as a continuous problem where you could basically have some kind of prior and then, some kind of Gaussian processy kind of thing that would capture some version of that information. Because there are definitely examples where it's true that like there's local things change with some model of like there's sometimes discontinuities, and then you've got to sort of explore and find them. Yes?
So you're learning on instances, but are you giving any thought to generalizability of features from geometry or something?
Yeah, so this is, I'll wait. So this is just showing after we do the learning, we pick up this ruler in the middle because we tried different graphs and that one worked better. And now it kind of survives the shake. And at this point, we are aggressively instance-based because I think that it's really important to make something that works and actually be able to pick up these objects. So I was going to show the shake, I think. He's going to smile. Oh, he's going to smile when he puts it down. He's like, yes, I got it. The reward function works. So the thing is, if we are able to collect this data and we collect this data autonomously, it gives us a potential to scale up the whole data collection effort. So this is sort of showing our evaluation, practicing picking up these different objects. And what we're doing now is gearing up to collect a lot of data about a lot of objects. So this is showing, there's like, I'm never sure whether to show the music. The soundtrack to this video is like the Hall of the Mountain King.
How important is it that this is done in the real world? I mean, could you do this all in CG?
I think it's very important to do it in the real world if you want it to work. So if we had a perfect simulator, then yes, you could do it in simulation. If you had a perfect simulator, you could also, the problem would be solved. Because if you could put the world in your perfect simulator, you could try stuff in simulation really, really quickly and then, do it. And you could do lots of learning, you could do deep learning. The problem is getting that perfect simulator. Yeah. And so I think that there's irreplaceable information in the real world that lets you build the simulator. Like if we're all supposed to be doing physics, that's great. Then let's collect lots of data and assess whether our physical models are good and have we picked the right constants and how are we doing friction and what is the interaction between the rubber tape that my student likes to use on the gripper to give it more friction and this particular plastic ruler. Like that's not something that's easy to put in a simulator. So this is showing the sort of quantitatively, before we do this learning process, we pick up this data set. This is our particular data set of objects that we picked. We get half of them. And after learning, we get 75%. And if you saw the video go by, this is from worst to best. So from about here on, we're 8 out of 10 picks are better. Some of these are really hard. So it's kind of bimodal. There's some really, really bad ones, and there's a bunch of really good ones. And we know what worked and what didn't work. So
it's interesting because it's not completely obvious to me what is.
Yeah, I can answer questions if you want to know. This we filled with water.
Okay.
To make it harder, because this one and this was also partly selected by us to exercise the system. So we were trying to get a diverse set of objects, but we wanted it to show that it could improve. So this one, its first grasp was this is a sippy cup, the lip of the cup, and that worked great. And it didn't. So I was like, oh, it's not going to learn. That sucks. So we filled it with water, and I hoped it would learn to go to the handle to get a better grasp, but. It did not, and it slips out a lot when it's filled with water. Yeah.
You said that the silver object with 2 handles was very hard, but on the right-hand side, yes, this one.
Yeah. So this is one that moved.
This one?
So it moved. So if I should make this picture with the before. It started out hard. After the learning, we learned to go on the handle, and now we can do it. We can do it pretty well. Yeah.
So it has 2 arms. Do you use both arms in some cases?
So you can see in the video, it's like. It's practicing with both arms. So right now, we treat them independently. But I'm really interested in learning things so there's our vanilla bottle, unscrewing this bottle. So you need to hold it with one arm and unscrew it with the other arm.
I was thinking with that big plastic thing, it would be easier with 2 hands.
Yes, the big plastic thing was actually a stupid bug. So when we test that we've released the object, we basically close the gripper and make sure that we can close it all the way. And we move up to a particular height and then do that test. And we didn't move up tall enough. And so it thought that it couldn't put it down. So it actually picked up that object pretty well off the bat, except that the reward function test wasn't very good because we didn't move up high enough. But we don't want to take it out because that seemed like cheating. Okay, so in terms of using 2 arms, what we're doing now is trying to scale this whole thing up to collect lots and lots and lots of data. So there's the COCO data set that you guys have, where people take pictures and then annotate, and then train computer vision algorithms on it. But that data set consists of a human photographer selecting the image, and then you get to see each object one time. Maybe there's probably exceptions to that, but like most of the time, you see each object in that one frame, and then it's gone forever, and you never get to see it again. In this data set, and the data that we're collecting, you get to see each object from multiple views and multiple different angles, and you get to pick it up and know empirically where this robot with this gripper, what its pick success rate was. And so what our goal is to scale up the data collection to collect a corpus that's like this for 1 million objects. It's computer vision scale corpus, where we really know a lot about each one of the objects in the corpus. And if you imagine having access to that data set and then trying your favorite deep learning algorithm to do some of these tasks like grasp point prediction, when you have some of this empirical success, or trying to learn a model of physics, you can actually test empirically how well it predicts what you're observing in the data set from this experience in the world. I think it will give us a new basis from which to approach all of these problems which we all care about, to train category-based methods to come in and see a room that you've never seen before. And in the meantime, by taking an instance-based approach at the cost of the robots, not your time, but the robots' time, you can have some of this robustness now using these instance-based algorithms.
So if you wanted to go large scale, have you thought of just going to Mechanical Turk with an image and saying, if you were to grasp this object using 2 fingers, where would you place your 2 fingers?
I was just going to say that, to get the language data tied to where you're...
So people do that. So like Sonia Chernova has a crowdsourcing process where people actually move the robot's gripper around, and then
you don't even have a robot. You say, if you were a human and you were to pick up that object with 2 fingers, where would you place?
Where would you pick it? Where would you?
Or you show the video of the successful pickup and ask what part of it was being grasped.
You could do that too. I'm just thinking, how can you get like 100,000 training examples or something like that? like quickly. With different
grasp points and stuff.
A variety of objects.
I see. But the question is then where do you get the images of the object?
You have the video of
100,000 objects. Different objects.
You can do search for a lot of small objects.
I see. You're talking about just abstract.
Just say you go to ImageNet, you get all the small objects on ImageNet, and then you send them to Mechanical Turk and say, find the, what are the 2 points that you
annotate me the grasp points. Yeah. And then take some subset. Yeah, I mean I think that would be cool. Like we should probably do that too. I'm not aware of the closest thing I'm aware of is somebody who Sonia Chernova at WPI who crowdsourced grasp point annotation, and they actually tested it on a real robot. So they had the person drag the gripper in a simulator on Turk, and then the robot went in and tried to pick it up and grasp it.
On folks that have worked with real-world simulations, like how to pack a truck and things like that are kind of related work. People at a distance have tried to sort of figure out how to do physical things in coordinated ways. So it's interesting to think about the idea of just coordinating on things.
I mean, I just think there's something irreplaceable. I don't think that's a bad idea, but I think what we're trying to do is get. I don't know. Like I think like I was imagining that we would do this and we would
get. It's not really a bad idea.
But it doesn't solve the problem. All of the problem that this data set would be, because you would get the result of actually doing stuff in the world. So for example, we could do that, but then how would you, you'd have to somehow subsample some set of objects and try those graphs to know how good those annotations were. If you had this data set, then you could...
Then you have a 2D image, and then you kind of predict where the 2 grasp points are, and how well that would work, I don't know.
Okay, maybe we should keep on partying on the idea. So how about we do this, find out where we're failing, and then have selective learn when it needs to go to a human being.
Or not even failing,
real world.
Not even failing, but when you've done it in a weird way. Like you probably have lots of successful grasps that are not what a human would do at all.
Another thing is humans might give you a lot of different, possibilities. Like one human will say here, another human will say there, and it'll give you different possibilities.
Yeah, and so in that perspective, you can take that as your graph proposal. So give us all of your graph proposals, we'll try them all and tell you which ones are good and which ones are bad.
The sippy cup, you would never, no human would pick maybe a toddler would, but a human generally would know how to handle it.
We expect an HCOM paper next year.
What's that?
We expect an HCOM paper.
I mean, I think that if you had this data set where you had like the sippy cup for multiple different angles, that's the other problem is that when you only get to see the object from whatever view happens to be an ImageNet, like that's probably not the view your robot's seeing, because your robot doesn't really know how the world works and is not very good at taking these pictures. And you want to go, like if they say pick up the sippy cup, I want to know it's a sippy cup, even if I see it out of the corner of my eye and it's occluded. So
the product charts don't have the variety, which
Yeah.
is what ImageNet did. Yeah.
that's right.
Maybe we should Coco and just do like real world, like dogs and things.
And Coco, the images are, the objects are lower resolution, so then I get worried
Yeah.
as well. So really,
And the
you want
dogs.
like high resolution objects of
Yeah.
a lot of random objects from
Yes.
different angles, which is people don't take photos.
People
like
don't take photos like that, but our robot does and
Yeah.
can. This is a robot that is made by Rethink Robotics. There's 300 of them in the research community right now. Most of them are sitting there doing nothing most of the time. These robots, these Baxters. It's sad but true, robots. So what we're doing right now is scaling up to collect that data set using the software infrastructure. So the idea is everybody's robot at night, when you're not using it, is doing object scan. You hand it a box of stuff, and it's doing the stuff. And maybe a lot of the objects it won't be able to pick up, but some of them it will. It'll collect these images, upload it to our database server, and then I want it to be the case that you can hit it with crowdsourced data too, so you can edit labels like the parts of the object and stuff.
So you said before
Yeah.
that CG data is not good because we don't have a good model of the friction and all that other stuff,
Mm-hmm.
right? However, let's say we have a lot of CG models of small objects. We can synthetically generate images, show
Mm-hmm.
them to humans and say, where should you pick these objects up? And use that as training examples on real images to then predict where those objects should be picked up. As long as the images look similar enough and rendered of high enough quality, that might actually transfer.
Yeah, people work on like SketchUp data and
Yeah.
trying to transfer it. I'm skeptical because like this is, I mean, how can I compare to this where it's like the real pixels, It's the stuff that
thing
you,
is here,
you know?
you're using humans to kind of predict the
Yeah.
point. You're
Yeah.
not doing any physics, right? You're just
Yeah.
using it to generate these images that we can't gather just
Yeah.
from, crawling Flickr.
Yeah, it seems to me that what you really want though is humans picking up the same objects and narrating what they're doing. That's the crowdsourcing that I would want, to now compare it to what you've learned as the right grasp point and see what's natural for humans. How do they refer to that?
You'd have to
That's
pay
a lot of
Turkers more
data.
money
It's
for
a lot
that,
of
yeah.
data, yeah, but it's kind of what you want, right? That
Yeah.
parallelism.
Yeah.
Have you tried looking for fingerprints on real objects where people pick them or stain
Yeah,
them?
something like that, yeah.
Yeah, we haven't done that.
Do you think there's also like, I don't know how much difference it is between our, dexterity and your gripper and whatever.
We're
people
way
would tell
better.
you how.
We're way better.
So
Yeah.
the question is the transfer.
And that's another
there.
question about human. I mean, like the way that a human would do it is not
Might not
necessarily
be
the best
the
way
way
for our robot to do it.
You could always put a camera on a cashier.
Yeah, at a grocery store.
Yeah, at a grocery store.
Yeah.
Yeah, that's
You
good.
know, or
Yeah.
like a Walmart or whatever.
I mean, I was just at Amazon, and they have cameras on all of their pickers who are pulling things off the shelves to put in boxes, and sort of seeing what they're doing with this stuff. But as an engineer who wants the robot to work, like this is something you can run on your robot and it will work. There's not any of these transfer questions because you're looking at your pixels and your motor torques and doing this learning. You can have pick and place, right? And then as a side effect or as maybe a target, you can also collect a lot of data. I think it is a unique data set that is not, like, I think that in terms of having multiple images of objects from multiple angles plus graph success rates is telling you stuff that I don't think you're going to get from SketchUp data. You don't know how much things weigh, you don't know the friction, you don't
Bananas.
the squishiness of bananas.
That's where you
So if you make like a deep learning model, you can actually be able to predict, like, if I pick it up here, will it, like, you'll have lots of these labeled examples. Tried to pick it up here and it slipped. I tried to pick it up here and it didn't slip. And you can imagine training some kind of thing that learns that. I don't think you could do that from SketchUp data, for example.
Oh, yeah, I was just gonna, I guess, mention more about, like, this idea of training for humans. I was thinking that it might be possible to have, like, children play with toys.
Yeah.
You could do this in your lab, like, this looks
Yeah.
like, I mean, I've done work like this too, where you
Yeah.
just go through your house and you're like, I'll take this
Yeah.
object and that
Yeah.
object
Yeah.
and that object. But it seems like you could actually have kids play with these very toys and the
Uh-huh.
robot can just sit and watch, which is a bit creepy, but
Uh-huh.
could learn a lot about how
Yeah.
the kids are grabbing, and in
Yeah.
a way that might, I mean, like
Yeah.
around 2 or 3, that might translate well to.
Yeah, I mean, another next step that I want to go to is not just pick and place, but like these things. This is a peppers grinder. It squeezes, this cap unscrews, and my son knows all that stuff. Like if you hand him the vanilla bottle, he will try to unscrew it and get vanilla all over everything. So it would be nice if the robot could also collect information, could do those actions as well. And I think that an approach where it somehow has proposals from maybe this human data about what are affordances of objects, or pick your favorite deep learning model and train it on whatever data you want and crowdsource it or SketchUp or whatever. But then let's try it out at a large scale on lots of real objects and see if we can learn from that. And build lots of maps. Like I did this, and guess what? It actually worked. It actually really truly did open this vanilla bottle. Like this is a fact about a change in the physical world that I don't think you're going to get from just images, because you actually put some torques on something and track the success. So if you imagine that we scale up this effort over time with more complex behaviors and more complex manipulations of objects, then I think it would be really cool to learn things like that. The ways that things move and the ways things rotate and tool use and all that stuff.
You probably don't need to learn for white out.
Yeah, I should. There's three more things.
Yeah. Sorry.
Oh, no, that's not.
Okay, so that was like, how can we have robots robustly perform actions in real world environments? We're not at this shelf yet, but in my lab, if you bring something in that fits in the robot's gripper, we can scan it, and in about 20 minutes, we can usually pick it up. And we have pick and place where you can pick it up and put it down somewhere else. So the next thing that I'm going to talk about is carrying out complex sequences of actions in very large state action spaces. So for example, something like building IKEA furniture, the robot might want to ask for help, like please hand me the white table leg. Or if you're a forklift, one of my favorite examples from the Turkers was, how do you pick up a dime with a forklift, a dime? So anybody want to guess how? With the forks. With the forks. You put the dime on top of the forks, just like a pallet.
I've seen this, I just forget how they did it.
Yeah.
It's this. Move the two arms to both sides.
You cannot, in this forklift you can't. You put the forks down on top of the dime, and then you slowly, here's the instructions they gave me. You slowly drive backward, and it flips to be on top. So raise the forks 12 inches, line up either fork in front of the dime, tilt the forks forward 15 degrees, pull the truck forward until one fork is directly over the dime, completely lower the forks, put the truck in reverse, and gently travel backward a foot. The dime will flip backwards. This was from a person on AMT. This was when a person on AMT who... What did you...
I said this is like the last day of your training program. It's like everyone...
That's right.
The first day they say, and the last day you'll be doing this.
Yeah.
Just keep your eyes open. Keep your feet on the pedal.
That's right. The person who gave me this was a worker on AMT who worked in a warehouse, and he told me that they use this to haze new forklift operators to give them a hard time. And what I want to point out is that you can say this in language. I can tell you in words, and like I use some gestures too. But like we all instantly understand what motions the forklift came. And if you knew how to drive a forklift, it might take you a few tries, but you could probably figure out how to get it to pick up a dime. And in the next breath, I can say unload the truck, and that's okay too. But if I give the robot this low-level action space, things are going to break. So we're exploring algorithms for trying to handle this so that we can accept commands at these different levels of abstraction. And to do this, I wanted to move to a simulation domain so that we could have very tall trees of actions, very, very high-level actions along with very, very low-level actions without making a robot that could do all of those things. So the domain that we're using is one that Microsoft now owns, which is Minecraft. This is a picture from the game Minecraft. So have you played it? Do people here know? So, what's that?
This was like the centerpiece of my family for like 7 years.
Yeah, so you're...
Yeah. Lived it.
You lived it. So Minecraft is a game. It's like Blox World with zombies. If you do AI, like and there's a very tall tech tree. So like there's a transistor block called redstone, and you can actually build a transistor in the world. Like a transistor is about as big as you in this world, and you can make things. People have made things like graphene calculators and ALUs and CPUs in Minecraft. But the sort of bread and butter is like you're wandering around a world much bigger than this. Is a 10 by 10 world. The real world, I don't even know how big it is. Like you can't find the end of it. It's like the Earth or something. And there's these zombies, and you can mine iron and make swords and all kinds of stuff, castles, and there's these dungeons, and I like to say it's AI complete, because if you can solve Minecraft, if you could like actually build a graphing calculator in Minecraft with your AI agent, then you could do everything else too. So what we're doing is trying to think about how to explore these problems with the state space explosion in Minecraft, because there's lots of data in simulation. You can imagine there's lots of language data about it, and it's a great example of this sort of state space explosion. So here's one of the first problems that we looked at. We called it a bridge problem. So the idea is you can do any of these actions: move, place, destroy, use, jump, rotate, look, craft. You can pick up any of these blocks, and your goal is to get from here to here. And you can't walk across the trench. You can't jump far enough to get across the trench. So what you're supposed to do is pick up one of these blocks, put it in the trench to make a bridge, and then walk across the trench. But if you take a sort of breadth-first search approach, you spend all your time in these parts of the state space. So this is even a simpler version, where we gave the agent 2 blocks it could place, and it's exploring all of the places those 2 blocks could be, and then trying to decide if that would help it get across the trench, when what you really want to do is make a bridge and then be at the goal. So the way we approach this is by formalizing this as a machine learning problem, where you sample as a Markov decision process. But in regular like RL, you basically, who's seen Groundhog Day, the movie? Yeah, regular RL, a lot of the work in regular RL makes an assumption very similar to the movie Groundhog Day, where they basically reset the agent to the same initial state over and over and over and over. And then the agent gets to learn. And they learn things like so Bill Murray learns things like, there's a scene where he like robs a bank, and he knows what car is going to drive by when, and they're going to drop the quarters, and their backs are turned, and he walks up and picks up the money and goes away. So he learns all these ridiculous things about the world. It's cool though, like not that it was good assumptions. It led to lots of interesting algorithms, and there's great work in RL under this set of assumptions. But this set of assumptions doesn't match a lot of problems in robotics and in the real world, because you will never see, in the real world, you never see the same state twice. Every day is a new day, and even if it's the same room, like everything is different. And so what you want is your agent to be plopped down in a state that it's never seen before, and still be able to take intelligent action, do what I tell it to do. So we normalize this as a sampling process, where we sample MDPs. You sample states from some underlying distribution and sample reward functions. You learn in small MDPs about what are good actions to take, and then you try to generalize that to larger problems and see if you can learn what are good parts of the state space to explore. So it's basically learning to do action pruning. So in the bridge problems, we learned that if you're trying to move somewhere in the environment and you're not standing near a trench, don't place blocks. So cut out all these branches of the search tree, because that doesn't help you most of the time. And this is probabilistic, so it's not like this is illustrating it as red and green, but in reality it's kind of soft probabilities. But it basically concentrates the search in the good parts of the state space. And it enables our agent to solve these bridge problems, much larger bridge problems than you can solve with even state-of-the-art planning methods that don't learn things about the environment based on the goals that they're trying to achieve. So this is published, it's going to appear at ICAPS in about a month. And we've also, this is like just our first stab in this area. We're really excited about hooking this up to language, because one of the motivations is being able to talk to these agents, and also doing model learning. So we're about to release a Minecraft mod that lets us run our RL framework inside of Minecraft, inside the Minecraft Java virtual machine, so that you can load the MDP state from the Minecraft chunk that you're in. So you can see all the block locations and stuff. And then we give a couple of example dungeons that are about this big, and you can run VI if you take out planning actions, and you'll find, walk across. It'll do all the grid world stuff. But then, you can try any RL algorithm that you want in this framework. And it's going to be like the Atari dataset, if you're familiar with the RL literature, where DeepMind and all that stuff just solved Atari. So this is the next thing, this Minecraft, where you have this huge, huge world and these blocks that you're trying to manipulate. Okay, Minecraft. So I have 5 more minutes. So I will just briefly talk about the social feedback loop. So this is sort of planning in these big state action spaces and how we're exploring that. So social feedback. So the idea is you have a large space of possible actions. In a typical kitchen, there might be 100 things, 100 ingredients that are just around in cupboards and stuff that you might be asked for. And the person will say something like, hand me the vanilla, and the robot has to figure out what actions to take in order to respond to that natural language request. So to do this, you have to map between words and language and stuff that's out there in the world. This is an example, a symbol grounding problem from the Forklift domain. And in my previous work, we did this by collecting lots of crowdsourced data and learning models of grounded compositional semantics, and showed that we could use this to make robots that interpreted natural language commands. This is some examples of that. So this is the forklift responding to a command like put the pallet on the truck, and then moving through the environment to carry out that command. This is the PR2 doing blocks world manipulation tasks. This is a ground vehicle that is following route direction requests through an outdoor environment, and up here is a helicopter about to take off, following natural language requests to look at stuff in the environment. So this was a lot of fun to do all these robots. But the problem with all of this work is if you watch every single one of those videos, what happens is somebody says something, and then a lot of time passes before the robot starts to move. And the problem is that whether or not the robot goes on to do the right thing, you've sort of already failed by the time the person has had to wait even a few seconds, because they have no idea if the robot is understanding them. They might try to repeat themselves. What we want is something more like what Dan does, where the system is always tracking what you're doing and producing feedback based on what it understands. So for example, so here's some commands that the people from Turk gave our forklift. Move the pallet from the truck, where there's 2 pallets on the truck here. So it's ambiguous. Even these unambiguous ones here, the offload the metal crate, so that one, if your language model is bad or you couldn't figure out that metal maps to these perceptual features, that may be ambiguous to the robot. And the person, not knowing how the robot works, will have no idea why this command is failing. So what we're trying to do is make robots that can solve these problems. We like to solve the underlying problems, but we want to make robots that are robust to this type of failure by creating a social feedback loop between the human and the robot. So when humans are talking to each other, they are constantly tracking what the other person is doing and trying to figure out if they understand, and they're nodding their head or they're looking confused. They'll stop the other person if they don't understand. And this feedback loop is what I think one of the main things that causes human-human interaction to be so robust to failures, because we are not open loop. We are operating in a closed loop way. So this is a study from Herb Clark studying human-human interaction, where one human was instructing another person to assemble structures out of Legos. And if they basically turn off feedback at different levels. So if they no longer share a workspace, they can still talk to each other. They're 2 times slower at carrying out the task. And if they turn off feedback, so they basically give the listener a recorded set of instructions, and they can stop and play back the recording, so it's not like they didn't hear it, they can go back, but there's no feedback. They can't ask questions or look or things like that. They make 8 times as many errors. And this is human-human interaction, where human speech recognition system, the human speech recognition system in our head is like pretty good, right? So we hope that they're able to understand the audio and stuff, and yet even so, feedback makes a huge difference. In the case of robots, where their perceptual abilities are so much more limited than what people do, we might hope for an even larger impact by having some kind of feedback mechanism. So to do this, we're working on methods for incrementally interpreting language and gesture from a person at a very high frequency. So this is showing the sort of basic idea. Here, the state, if you think of this from like a dialogue perspective, the state is which object the person wants. The belief state is a multinomial over that, so which one of these 4 objects is going on. And we're updating the belief state word by word and gesture by gesture at 14 hertz, a very high frequency, in order to very quickly and basically continuously subscribe, right? We're publishing what the robot thinks about the person's intentions in real time. Yes?
occurs to me, one thing robots...
How much over can I go? It's now 2:30.
We're until 3, I think.
Yeah, we can have joyous discussion, you go to 3 o'clock.
Is that okay? Okay. Okay.
So
It occurs to me, one thing robots can do better than people is point a laser at an object and say, is it this one, right? Even
Yes.
10 feet away.
Yes. Right. So I think that's one of the other glorious things about social feedback is if it, I mean, we don't want our robots to be annoying. Like, is it this one? Is it this one? Like, if it's too bad, it'll be very frustrating. Yeah. But if we can create that feedback loop and successfully recover from these failures, we will create labeled training examples out of that process. So if we fail to understand something and then they disambiguate with a gesture and then we get it and we know we got it, we can go back to that language that we initially misunderstood and try to fix it up. Use our, deep learning is a thing now, right? Or use Dan's system to retrain your model and improve the performance in these real interactions. Or learn the specific language and gestures that a particular person likes to use in different situations. Yes?
You mentioned gestures mostly, but gaze recognition is absolutely fundamental.
Yes. Yes. So I was talking to Dan about this. We tried. It's silly. So the results that I have are language and gesture. We tried face. We have numbers for face, gaze direction, and they suck. And they suck because our gaze tracker sucks. So we think that. So I believe you enough that we actually tried it, but I took the numbers out because it didn't work for an uninteresting reason. So we are exploring better face trackers, and I have the hypothesis that will also help. So yes, that's right. The model, this is the model we're using. This is a generative model. Jason was explaining to me that the state of the art now is discriminative models for doing this kind of state estimation for dialogue. But in the state of the art is also that they get to train and test their models on existing data sets that were collected by somebody else. So Jason is one of the people organizing this for the Cambridge data set, where it talks about like people are asking about restaurant recommendations in Cambridge, England. Before that, there was a CMU data set about bus schedules, and people train discriminative models on these data sets. And of course, there's no models for my kinds of tasks. So we started out with a generative model, and Jason said, I'm really excited about this. Jason said we can use, like the way that you collect the data in the first place is you take a model that kind of works and you run it on lots of people, and that's what you use to collect the data to train your discriminative model, which is now beating the pants off all of the generative models. So this is our generative model for state estimation. And the idea is the hidden state is what's in the person's brain. The observations are language and gesture. And you can add face, you can add gaze, you can add everything else that you want to. And really, I believe that discriminative would work better, but we don't have the data, and we're excited about trying to collect that data. But even with a generative model, you can get quite good results. So here's an example of what it looks like when it runs. So here he's pointing. He says, please hand me that, and then that. These pointing gestures. And what you notice is that the model is updating as an animation because it's happening at such a high frequency that these probabilities are sort of moving up and down in real time in a lively way, right? So here, I'll show you another one. So he says, I would like a bowl. So as soon as it sees bowl, both bowls jump up. Then he points, and it saves the probability. It doesn't start from scratch because it knew it was both, and it disambiguates with the gesture. So we're combining multimodal information from language and gesture to do this. You can also get compositional semantics, poor man's compositional semantics, little bits of compositional semantics out of this. So I would like a spoon, the plastic one. So here, each one individually is ambiguous. I would like a spoon is ambiguous. I would like the plastic one is ambiguous. But because the model is saving information through time, it's able to get the plastic spoon because it's sort of, and also take into account that this is happening relatively close in time. If a lot more time had passed, things would have decayed back to neutral, and then it would not have incorporated as much information from the past, which is kind of what you want in this. And then you can have, if you have an ambiguous gesture, so here he's going to point ambiguously, deliberately to sort of demonstrate, and then say the plastic one. And again, the gesture and the language were ambiguous, but you combine the information to get better performance. So we can sort of show you a couple. We're just starting to explore the feedback now. So like the idea is you have this bar graph of things. Maybe I'll show the video. You have this bar graph, but we don't want, maybe we should show the bar graph to people, but like, it's hard to for an untrained person to interpret a bar graph like that. So now what we're trying to do is render this graph on the robot through gaze of the robot and facial expressions on the robot and pointing gestures and looking gestures on the robot to try to say like, well, if I'm confused between this spoon and that spoon, it should look back and forth between those two objects. And then the person's going to get some information from that about which of the two the robot thinks about, and then be able to provide that targeted feedback. So I can show you some examples. This is like our earliest prototype, where it's basically pointing at the object that it thinks it understands, and we have like this fixed face. It's either happy or sad. This is a more recent video where it's actually going to deliver the object. So he's saying he wants the brush, and the robot moves and delivers the brush. And we're exploring more mechanisms now to do this. And I can also show our quantitative results of this. So if there's just 4 objects then in this evaluation, where we had people come in and they talked to the robot, we told them, tell the robot that you want a particular object. We pointed out the object with a laser pointer so that we knew which one they were talking about. And we said, tell another person what you would do with language and gesture to pick up the object. So random is 25%. If we use language only, we got 46% right using the Google's feature recognition system, and we mic'd them. So we didn't have a far field microphone. If you use gesture only, we got 80%. This is pointing gestures. It's like a Gaussian model of pointing with a covariance. The really cool thing is if you combine language and gesture, you do even better. So you get 91% with the multimodal information. The language results surprised speech recognition people. This was from the workshop. Actually, I didn't have the answer. I don't know if you. I looked up why. I didn't have a good answer at the workshop. The reason is that we told them to talk as if they were talking to a person, so they will often point and say that one. And we were only using the language without the gesture. So the speech recognition worked. It wasn't just speech recognition error. It was that they said something that was ambiguous without the gesture. So these results are showing that this model is improving from using this multimodal information. And our next step is this is going to be our baseline. Yeah.
These numbers seem like they would be very dependent on the kinds of objects, the number of objects, and
that's right.
I could imagine that language would become more and more important if you had a lot of very similar objects.
That's right. That's right. So what we're doing now, this is with just 4 objects. What we're doing now is trying to scale up to like 10 or 20. And I expect the performance to drop and the language to matter more in these different situations. And then we're going to have, like the goal is, this is the baseline, and if we turn on different types of social feedback, how do things change? So can we, because this is too good. Like this, we might get 10 points better or something, but I want the baseline with no social feedback to be around 60. So we're exploring different versions of this task, harder versions with more objects that are farther away, so it's harder to point. And then once we get that once we have a task where that's bad, then we can try adding social feedback and see if we can get back up to 90 or 100. Yes.
Is it actually learning materials, plastic, metal distinction?
In this task,
is this something that's actually?
No, in this task we give it. It's a generative model, so we give it. I'll go zip back. So we do not need training data, but we do need this distribution. This is the probability of the distribution we need is this one. So the probability of L given X. So X is the true object. Let's say it's the plastic bowl, and L is the words that they use. That's a language model conditioned on the object. So we write that down right now. So we say, okay, plastic bowl, color, and if they say word, like we do a pilot test. So if they say words that we didn't have, we add them in. And collect it that way. If this plugs into the scanning system, so like to get that, you could upload the images to Turk and have them type down descriptions and count up the words, and get a unigram language model. Or you could collect lots of people interacting and pointing at these systems, and again, you have either use a generative thing to get that, or have a discriminative model that would learn basically that these are the words people use to describe the objects. And we don't, and it's instance-based, so we don't know that what plastic means. But again, if you had this scale, if we collected that data set of 1 million objects and Turked them all, you could then have plastic from many different objects and many different viewpoints with different reflections and stuff, and try to learn a visual plastic predictor that might work.
So far, material detection doesn't work super well unless it's really closely related to like color.
Yeah.
So like wood, we can detect wood because it tends to be brown as well.
Reflectivity, for example, metals versus plastic.
Yeah, I don't really know that plastic detection works very well.
People experiment with more sensors on their gripper, grasp, whatever.
Yeah.
The pressure sensitivity.
Yeah, so we have basically like just pressure, but people put different versions of skin on their grippers. So we're collaborating with MIT, who has a soft hand made out of silicone, and they're putting more sensors on it. And people do that. They do that actively to do grasping. So like you can, like even if you can't see, you can kind of feel what the robot will feel and predict movements to get a good grasp. And again, if you put that on a back, we're collecting data from them now, so that can all be stuff in this data set, you know, and it may not have as much with that particular hand because there's not. So one of the things about getting this data set is the Baxter's existence. Like there's 300 Baxters, and the gripper that they have, like Rod, the person who runs the company that made this robot, told me he put it on the robot to piss everybody off and make it so that they invent new grippers. So it is definitely not the best gripper in the world. There's a lot of limitations to it, and there are other alternative grippers. But by using their gripper, anybody with a Baxter can just use the software with as low barrier to entry as possible. So that's what we're aiming for. Okay, so back to the videos. All right, and then this is just showing the face that we're working on. Smoothly transitioning between confused and happy in kind of a sine wave. We set the position, the confusion level on this face based on the entropy of the underlying distribution. So we are doing something kind of animated, but like it's being driven by something real about what the robot's perceiving about the environment. And I really liked your face was so much better with the eyebrows and stuff. What's that?
I pointed you to our ICNI paper on this. No?
No.
We use HP also for the expression control. It wasn't as smooth though. Also relates to our work. So we had a project called Deep Listener about 10 years ago where we used Hal's eye, and we scanned it and it looked like glass and the redness. But it went continuously between green for I'm okay, I'm getting you, to yellow, just hang on, slow down, getting confused, to red, which is like hang on, let's back up. It was very smoothly. That was kind of the
I'm trying to find so we're collaborating with some people from RISD who are helping us with face designs, and I'm trying to get my head around the literature. I've been talking to Bill Gay also. I don't see our contribution as like this is the best face we should all be using. It's more like I just wanted some way to something that I could set with entropy, and like the eyebrow thing that was in your face.
The paper,
you know.
Okay.
Great.
But it was really a full face modeling with lots of effort to get like a confused. Human-like face.
There's also different kinds of confusion, like confusion on the visual channel versus you might also have confusion about the gesture.
We use similar notions of entropy for confusion, different kinds of entropy.
Makes sense. I think that's awesome. And like and this is just our first step. Like entropy seemed like the obvious place to start, but we're also like looking. I think looking is going to be very important. So like looking at the objects. And
I think one of our challenges is once you get to the real, like to the more complex tasks, when we're talking about the debug mode, you know, one of our challenges in some of these more intricate systems, you have so many uncertainties. And the question is, you cannot reflect all of them. So
you just look like what?
You kind of need a model of how the person works and what they would understand of that.
Yes.
You know, so
it
gets interesting.
Right, and it goes, so we talk about in future work, we did a little bit of this, but there's not just confusion, but what does it look like? What does a face? What does the robot express when its confusion has been just resolved? Or when it's surprised by it. Something like confusion. And so it communicates that and ground on that.
So my hope is that there's like some kind of POMDP-ish thing where like your action transition something in the person's mental state about what you think the robot thinks, what the person thinks the robot thinks. And then, you know, maybe that if we do that right, it might tell you something about that you should look relieved, because then they're going to know that you're no longer confused, and that's good. Like, you want them to understand what your mental state is.
One can do a full modal belief system like that, or you can also just assume some independence, and you have notions of what a surprise is that's a little bit independent of having two POMDPs running. But it's okay.
Yes.
I mean, I can see the.
Yeah, my students and I are kind of having that debate right now. Like, I think the POMDP is really elegant, and they're like, no, we need to make heuristic approximations, like what you're talking about, in order to make it practical. So we're sort of exploring that. You had your hand up for a while.
Have you come across Chernoff faces? Which are a way to plot multi-dimensional numbers by people having all sorts of funny faces.
No.
No.
Well, Michael Cohen had similar. So Michael Cohen had his own set of dimensions. So Chernoff bases were these, the famous. Who's the statistician that did that?
Chernoff. I would suspect.
Well, okay. You're right about that.
I'm just guessing.
Is it Chernoff or faces?
Yeah, it was faces study of Chernoff. So at least he had like the 3 dimensions, but Michael Cohen had a kind of a cool, his own set of dimensions he wanted to, he picked, and it would be nicer in some ways for our applications than Chernoff faces, but it's cool. The same similar thinking.
It'd be interesting to talk more about, because we've been hitting how do you control, what are the levers that you want to control? So confusion level is just one dimension, but confusion and surprise, and I talked to one of my mentors about this, confusion is bad, right? He said, no, I'm happy when I'm confused, because I'm a researcher and it means I'm about to learn something. So so it's you want to be confused and happy, and confused and sad, and confused and nervous, and what are the levers that our underlying model should support in order to express all of this stuff.
I guess we're sort of in more of a discussion mode now.
Yeah, this is the end. Robots that perform actions.
So we've been working on as part of the work with the intern here 2 summers ago, on a really rich, if you're interested in, again, barring concern about the uncanniness of various kinds, I take it too seriously, a nice avatar with expressions of various kinds, and a whole authoring toolkit for these, and we want to field it out to academic partners. So it might be a fun thing to field out to Stephanie's team. Jamie's stuff. We're actually building kind of a whole environment that we want to share out, get make shareware and get more.
Yeah, I mean, I have one student from RISD, the Rhode Island School of Design, and another undergrad who's from animation, and a professor from RISD, who are all helping us with the.
And then there's all these interesting design questions, like even when you start with. When we did the avatar by my door upstairs. We had all these different charcoal sketch version, line drawing version.
We are.
Just a light bulb.
Come to my lab and you'll see.
Just a circle spinning like the Cortana X.
The one we're running now is actually much more abstract than that face, like the one that the slide one. So they felt that was less.
Because between the HAL lens scanned in this morphing between red and yellow and green, it's like everyone kind of after a while you sort of map your mind to it. You're looking at this thing, you're talking to it, it's changing colors.
It starts to seem like it has feelings.
Yeah, like eyebrows. Looks like eyebrows to you. Between that and the full we're sketching a really human-like face. We're working on the muscles. And it's kind of an interesting world there. I'm not sure RISD fits it.
Yes.
But somewhere maybe more on the HAL side.
Their approach was to map out the space. So they put up these posters in my lab, of all the robots they could find and what their faces were like, and then they had us all draw faces on our whiteboard. They let the sign draw a face, and everybody who walked by could draw examples of faces, and then they make mock-ups and they put it up on the robot, and we decide how we like it and iterate. So we have a large space of faces that are around now, and the one that they've been moving towards is more abstract and cartoony than the one that I showed, but still has a face, like eyes and a nose and a mouth and stuff. So we'll see where they go. So that's the talk. So robots that robustly perform actions in real-world environments, carrying out complex sequences of actions with the Minecraft stuff, and then actively coordinating with people to establish a social feedback loop. They're all kind of separate right now. These two connect together, but my hope is before I get tenure, they all connect together. So you have complex actions in real-world environments, and you're giving natural language commands, dialogue, question answering, all in collaboration with the person. So thank you.